Hi folks, this is a brief review of eigenvectors and eigenvalues from linear algebra. I think that's part of the prerequisites, so theoretically you're supposed to have seen this, but it never hurts to review it briefly. So the context we're working in is linear algebra, where we're working in a vector space, a finite dimensional vector space. So x is some vector, and x is some vector, and A is some matrix, a square matrix. So when you multiply A times x, you produce a vector of the same dimension as x was, right? So basically A is a linear, you can think of the matrix A as a linear map from this vector space to itself, right? Any vector multiplied by A produces another vector in the same vector space. And then an eigenvector is a particularly simple example of the way this matrix or this linear mapping could act on the vector space. X is said to be an eigenvector of the matrix A, or the linear mapping A, if A times x is equal to lambda times x, where lambda times x is simply the a scalar multiple times the original vector x. In other words, the lambda is a scalar, and therefore one way to think about this, let's say, is that over here, if this is the original vector x, and then A times x is a scalar multiple of x, that means it's parallel to it, right? That means you can get to A times x by multiplying x times some scalar, which means it's basically in the same direction as x, although it might be in the exact opposite direction, right? If the sign of the scalar lambda is negative, then you could go in the opposite direction. But basically, x and ax are parallel. And that's the simplest kind of linear operation you can have, where you just map vectors x to the same subspace, to the same line that x is on. And let's see. So if you can understand how a matrix operates on its eigenvectors, which is relatively easy, and if you can understand how the eigenvectors break up the entire space, putting the eigenvectors together, if that can be seen as making up the entire vector space, then that gives you a good way to understand how linear mappings work, right? How the matrix A operates on the vector space. Okay, so by the way, one thing that particularly interesting for us is that in this case, if x is an eigenvector with eigenvalue lambda, the lambda is called the eigenvalue of the eigenvector. It's whatever you have to multiply, whatever scale you have to multiply by. Then it's also true for powers of A times x. So in other words, A to the k times x, that's just multiplying k times x. Each time you do it, you pick up one factor of lambda, so that's just equal to lambda to the k times x. So if you have an eigenvector with a certain eigenvalue, then it works for powers of A as well. Okay. It's worth pointing out that the set of all eigenvectors for a particular fixed eigenvalue lambda, they actually form a vector subspace, which means that these vectors that all have the same eigenvalue lambda, you can add them, or in fact take linear combinations of them, and you still get another vector in the same vector subspace, meaning that it will have the same, it will also be an eigenvector with the same eigenvalue. Right? So it's very simple to show that if x is an eigenvalue with, an eigenvector with eigenvalue lambda, and y is also an eigenvector with eigenvalue lambda, then if you take any linear combination of x and y, when you multiply by a, you're just going to pick up a factor of lambda in both terms. So that shows that ax plus by is also an eigenvector with the same eigenvalue. So that's a useful thing to know. Okay. Now, how do you actually calculate eigenvectors and eigenvalues? Well, the first thing is that the best way to do it is to first compute the eigenvalues, and then once you know the eigenvalues, then you can work through each eigenvalue in turn and calculate the corresponding eigenvector. So to calculate the eigenvalues, we start with this equation ax equals lambda x, and rearrange it so that we have the x terms on one side and you factor out the x and you get this form of the same equation. Right? So a minus lambda times the identity matrix I times x equals 0. And notice this 0 is boldfaced because it's a vector of zeros. It's a vector the same size as x, and it has all zeros as its entries. Notice that we had to multiply lambda times I in order to turn this into a matrix. Right? So lambda times I is a matrix that has the number lambda on its main diagonal and zeros everywhere else. Right? So I have to do that. That has the effect then, that matrix has the effect of just multiplying anything by it, by lambda. And it multiplies each row of x by lambda. So it performs the same operation as the scalar multiple lambda times x. Now, if a minus lambda x times x is equal to 0, that means that a minus lambda, did I say a minus lambda x? A minus lambda I times x is equal to 0. That means a minus lambda I is singular because it has a non-trivial null space, right? That means that x is a null vector, so it's in the null space of a minus lambda I, and so that means lambda I must be a singular matrix. And so one way to figure out what lambda is to use the equation that the determinant of a minus lambda I equals 0, because that's one way you can tell that a matrix is singular. A square matrix is singular if its determinant is 0. In fact, if and only if its determinant is 0. So let's see. So let me do an example. Right? Let's find the eigenvalues of this matrix over here. A equals 5, 2, 3, 4. First what I do is I form the matrix A minus lambda I, and that means you simply subtract lambda from each entry on the diagonal of A. Right? Because lambda, as I said, lambda I is just a diagonal matrix that has lambda on the main diagonal and 0 everywhere else. So this is A minus lambda I. And then we take the determinant of this. Well, of course, it's very easy to take the determinant of a 2 by 2 matrix. You just multiply the main diagonal, the product along the main diagonal, and then subtract off the product along the other diagonal. Right? Unfortunately, it's not that simple for bigger matrices, but for 2 by 2 matrices, it works out very nicely. So we get this equation, 5 minus lambda times 4 minus lambda minus 2 times 3 equals 0, setting the determinant equal to 0. Well, if we multiply this all out, rearrange terms, we get this. It's a nice, simple quadratic equation. And in fact, this one I set up so that we could solve it without using the quadratic formula. We don't have to, we won't get any radicals or anything. It has a nice whole number answer. So it turns out that the solution is lambda equals 2 or 7. So there are 2 solutions. And in general, you'll have n possible eigenvalues for a matrix of size n by n. Right? So there'll be basically a distinct eigenvalue for each dimension of the vector space you're working in. Of course, it could happen that you could have repeated roots. So for example, conceivably, even in this small example, I could have had a quadratic expression here that was a perfect square, and then I would have had a repeated root. Right? So for example, I could have found, the equation might have been, the equation might have been, lambda minus 5 squared equals 0, and then we would have found that there was only one eigenvalue 5, which is a double root of this equation. And then things actually get a little ickier, maybe, and not all the theory we're going to talk about will hold true. However, the chance of this happening is basically 0. But the probability, if you write down a random matrix like a random 2 by 2 matrix like this, or even, even more so for a higher dimension square matrix, if you write one down at random, the probability that it's going to have a double root, right, that it'll have a double eigenvalue like that, is basically 0. So it's not something you have to worry about coming up in random problems in the real world, but it is a theoretical problem. However, we're going to ignore that, right, in what we talk about. Okay, now, so at this point we figured out what the eigenvalues are. So how do we use the eigenvalues to figure out what the corresponding eigenvectors are? Well, for that, we now go back to that equation again. We know that we're trying to solve this. A minus lambda I times x equals 0. Now we know what lambda is, and so this gives us a definite linear equation that we can solve for x. So, let's do it, for example, in the case when lambda equals 2. Then a minus 2 times I is equal to this, and you can see this is certainly a singular matrix, right? It certainly has determinant 0 because the two rows are the same. And then you want to solve this, you want to solve this equation over here. You want to solve this equation for x. Okay? So, you can do it any way you want, right? So we think of this as a matrix equation that we're trying to solve. So one way you learn to do this in linear algebra would be to use row reduction with an augmented matrix. Of course, one method you cannot use is a matrix inverse, because, of course, this is a singular matrix, so it doesn't have an inverse. Right? So that method is out, but you can use any other method you may have learned anywhere. You can convert it into a system of equations. I don't particularly recommend that, because I think the matrix method is easier using row reduction. So that's the way I did it here. And this only takes like 2 steps to completely row reduce it to this. And you find that of course, one of the rows cancels completely, because this was a singular matrix. And then when you translate the row-reduced augmented matrix back into equation form, you get this. And you can write the solution this way, where we think of y as being a free parameter. Y can be anything, but given y, then x must be equal to negative 2/3 y. And so we can write the general form of the solution like this. Right? So notice that there's infinitely many solutions, which makes sense because, as I said earlier, in fact, the set of eigenvectors for a particular eigenvalue actually form a subspace, a vector subspace. So of course there's infinitely many solutions, and you get one solution for each value of y that you plug in, right? Any value of y that you plug in. So just to check our calculations, let's take a simple value of y. Let's plug in y equals 3, and if we do that, then we get x equals negative 2, 3. Right? Let's verify that that is in fact an eigenvector of the original matrix A with eigenvalue 2. Well, if you multiply it times A, let's see, where was A? This guy, 5, 2, 3, 4. So if you multiply 5, 2, 3, 4 times negative 2, 3, what you end up with is in fact negative 4, 6, which is, as it happens, exactly 2 times the original vector x. So it worked. Right? So our calculation seems to have been correct. We came up with the correct formula for the eigenvectors corresponding to eigenvalue 2, and then you could do something similar to find the other eigenvalues, eigenvectors with the other eigenvalue of 5. Okay? Now, of course, things get more complicated if you have a bigger matrix, if you have a 3 by 3 or 4 by 4, or, 100 by 100 matrix. If you're doing real-world problems with, with real-world data, you might have huge matrices that you'd want to work with. And in that case, this method of doing it by hand and solving a polynomial equation is not going to cut it, so you want to use computer methods. So what I'll do next is, let me show you how to do the same calculation on Mathematica. Okay, here we are in Mathematica, and there are a number of quirks about Mathematica, or a number of idiosyncrasies that all computer languages have. You have to get used to. One with Mathematica is that matrices are represented as lists of lists, and lists are just curly braces delimited lists, right? So you just form a list of numbers, for example, by 1, 2, 3, and putting it in curly braces. That's a list of numbers. One other thing, in order to enter something in Mathematica, you either hit Control Enter, Shift Enter, not Control Enter, Shift Enter, or you can use the Enter key on the numeric keypad. So either way, but if you just hit Enter, it just creates a new line where you're working, but it does not read what you've been typing into the computer and process it. Okay, so this is a list of numbers. If you want a list of lists, you could do something like 1, 2, 3, comma, 4, 5, 6. So now this is a list of 2 lists, right? And you enter that, well, it still prints it just as a list of lists. However, you can ask it to print things in different formats. So if you notice there's an optional menu over here on the right. So if you click on that, you can ask it to display it as a matrix, right? So that's how you would display it in matrix form. You can turn this menu off if you like. You can hit the X key if you want. Let me see. Maybe I'll do that here though. Let me see. Let me display this. So this was our A matrix. Oh, we want to use it as a matrix. Okay, as a matrix, we want to display it as a matrix. Okay, so this was our A matrix, right? 5, 2, 3, 4. So I entered that. I gave it the name AMAT, A matrix. By the way, one other convention in Mathematica is user-defined things start with lowercase letters, whereas internal functions and constants start with uppercase letters, right? So slightly. It's a useful convention just to keep things straight, right? Your definitions as opposed to Mathematica's own definitions. Okay, so AMAT is this matrix, and if you want to multiply the matrix times something, let's make up a vector. For example, suppose I have the x vector, I'll call it xvec, equals. Now, I guess I want to think of this because A is a 2 by 2 matrix, right? I want to think of x as being a 2 by 1 vector, so I can multiply A times x. So let's do it that way. Let's say, I don't know, -1 and 3. Right? So notice I entered -1, which is the entry in the first row as a singleton list, and then after the comma I put the second row, which I entered also as a singleton list 3. And once again, we can display this as a matrix to make sure it interpreted that correctly. Yeah, so that's what we want. Oh, I should have called it xvec, not xvex. That's vexing. Okay. Okay, now we can multiply the A matrix times the xvex. Okay, I'll just go with it. Oh, I'm sorry. You know what I have to do? It doesn't know how to multiply those two things in the ordinary sense. What we actually want to do is matrix multiplication, which is represented by a dot, kind of like the dot product. Okay, so if we multiply AX 5, 2, A, which is 5, 2, 3, 4, times the x vector -1, 3. Did it do that right? I can't see it all at once, but I'm assuming Mathematica did that correctly. Let me just get rid of some of this stuff. Let me get rid of this kind. So, yeah, that's right. So, so multiply them correctly, got the answer, and you can display the answer as a matrix if you want. Yeah, so that's the correct answer. So, okay, so that's another tip. To do matrix multiplication, you use a dot, just a period, as the operation, right? Mathematica does not interpret ordinary multiplication as matrix multiplication. In Mathematica, if you want to just multiply two numbers together, you can just put a space between them. And notice it filled in a gray X, meaning it interprets the space there as multiplication. So if I enter that, I get 6. I could also have filled in a star, right? But just putting a space is enough for Mathematica to interpret as multiplication, which sometimes is inconvenient because sometimes you put spaces accidentally and don't realize it, and Mathematica interprets them as multiplication. So it's actually a good thing that they will remind you here by putting this gray X. It'll let you know when it's planning to interpret a space as multiplication. Okay, let's see now, what else? Okay, so now how do we find the eigenvalues and eigenvectors for a matrix? Well, there's, as you might imagine, there's a nice built-in function, eigen. Oh, by the way, Mathematica has a great online help system and a great command completion system, so we want the eigenvalues, so that happens to be the first thing that pops up here. So eigenvalues of the A matrix. Here we go. Eigenvalues were in fact 7 and 2, right? We computed that by hand. So it just gives you a list of all the eigenvalues. And then if you want to get the eigenvectors, as you might imagine, as you might have seen, there's also an Eigenvectors command, so I can use that. Right, and it turns out I believe that the eigenvalues and eigenvectors are given in corresponding orders. So in other words, I think the first eigenvalue that was given goes with the first eigenvector. So 1, 1. Let's see, is that right? 1, 1. If I multiply 5, 2, 3, 4 times 1, 1, yeah, I get 7, 7, which is in fact 7 times 1, 1. So that's right. And similarly, the eigenvalue 2 goes with the eigenvector negative 2, 3. So, yeah, okay, so it does all that for you. Incidentally, since we usually want to compute both the eigenvectors and the eigenvalues, you can use the command called Eigensystem, which computes both at once, right? It kind of makes sense to do it that way. So if you ask for the eigensystem of the AMAT matrix, then first it gives you the list of eigenvalues. This can be a little confusing to read, but the first list is the list of eigenvalues, and then the second list is a list of the corresponding eigenvectors. So this is a list of lists. The first list here is basically the eigenvector 1, 1 that corresponds to the eigenvalue 7, and the second list is the eigenvector negative 2, 3, which corresponds to the eigenvalue 2. Notice, by the way, that it just gives you a vector here as a one-dimensional matrix. It's kind of like a one-dimensional list, not as a 1 by 2 matrix, right? Sometimes that's a little irritating, but you can learn to live with it. If you want to check, I think Mathematica does understand how to multiply a matrix times a vector like this. So notice I put a space. Let me see. Is it going to do this right? Let's see. Yeah, it worked. No, it did not work. Oh, I see. Okay, maybe what I should do is dot. Ah, that worked. Okay. So what happens is that Mathematica, when you try to multiply it by this list, it realizes that you can't multiply a matrix by a list. So what you must have meant was to multiply this matrix by the vector 1, 1, and it reinterprets this list as a column vector, right? Sometimes it does nice things like that for you, and sometimes it doesn't, right? So again, you might have thought I did think, that it would interpret this, AMAT times 1, 1, as a matrix multiplication, the matrix times a vector, but it didn't, right? So you have to explicitly tell it you want to multiply using the dot operation. Oh, one other quirk about Mathematica I think I forgot to mention is that when you plug in inputs into a function, you use square braces, right? Normally in mathematics we use round braces to input values into a function, but Mathematica uses square braces. Okay, go figure. So that's something you have to get used to. So okay, let's really exercise it. Let's give it like a random matrix. So let's say a rand matrix. I think I can just generate a big random matrix by taking, let's see, random integer. How about that? Oh, good online help system here. Oh, let me see if I can show you this. Yeah, random integer. That's what I want. Random integer. Oh yeah. I think I can use it to produce. Oh, right. So it'll produce 20 integers in the range 0 through 5. Ah, I see. And I can also produce an array. Okay. So let's try that. So random integer. Well, first of all, I could produce a single random integer by. Oh, let me see. Do I do this? Yeah. And then I think this will produce a random integer. Oh, it's always 1. Okay. So if you don't give it an input. However, if I give it a 2, it'll produce a random integer less, between 0 and 2. Is that right? Okay. If I give it a 1, let me see, I think it should produce a random integer. Yeah, so sometimes you do get 0. So basically the rule is random integer gives you a random integer from 0 up to the number you entered, right? So if I enter a 9, I'll get a random integer between 0 and 9. Now I can also add a second input to tell me how many random integers I want. So maybe I want 3 random integers. It'll give me 3 random integers, each one between 0 and 9. Right? Or I can ask it to give me 11. Right? It'll give me 11 random integers, each one between 0 and 9. Or if I put in a list of numbers here, I can ask it to give me a matrix. So for example, I could ask it to give me a 5 by 5 matrix. Right? So this is a list which the random integer function will understand as the dimensions of the matrix it's supposed to fill in. So it's going to fill in a 5 by 5 matrix using the digits 0 through 9. So we get that. Okay, so there's my random matrix. Let's display it as a matrix. And there we go. It's a random matrix of whole numbers, 1-digit positive whole numbers. And then I can ask the eigensystem function to just compute all the eigenvalues and eigenvectors of this random matrix. Now, we should find that it has 5 distinct eigenvalues because, think back to the method we used to find the eigenvalues. You end up solving a polynomial equation, and the degree of the polynomial is the same as the size of the matrix. So we'll be solving a 5th degree polynomial, and then you're going to have 5 solutions. It's overwhelmingly likely that the 5 solutions will all be distinct from one another, but there is a small chance that there could be repeated roots, but very unlikely. Let's see. So when I evaluate the eigensystem function on this random matrix, it does indeed find that there are 5 distinct eigenvalues, right? This is the first list in the result is the list of the eigenvalues, and there are 5 distinct numbers in there. Notice, by the way, it's offering the values in both decimal form and also in exact unsimplified form. So when you highlight it, you actually get the unsimplified form. It's the root of, it's the 5th root, actually, of this expression, right? However, for most purposes, we're not going to care about the symbolic expression that represents the root. We just want the decimal value, right, the decimal approximation. But anyway, Mathematica does offer you both here, right? So you can see the exact value as well as the decimal approximation. Now, for each one of these eigenvalues, there's going to be a corresponding eigenvector. Now, the eigenvectors, again, because Mathematica is going to offer you both the exact value and the approximate value, this is a hideous expression that it gives you. This is the first vector. And it says that the first entry in the first vector is this number here. This is the first number in the first vector. This is the second number in the first vector. This is the third number in the first vector. This is the 4th number in the first vector. And the last number in the first vector is just 1. So this whole mess here is in fact the first vector, right? And it's given in both decimal and unsimplified form. That's why it takes up so much space. And then the second vector, so by the way, this was the first eigenvector, therefore it corresponds to the first eigenvalue over here. And then the second vector is over here. Let's see. Yeah, here's the second vector, and then the third vector down here, and oh yeah, there it is, the third vector, and now the fourth vector, and then finally the fifth vector, right? Each corresponding to one of the 5 eigenvalues, right? Now, it's obviously very difficult to work with that mess. What you would probably want to do is say, maybe we'll call it the Eigensystem, right? I'll say the Eigensystem is equal to this output. By the way, because sometimes the outputs from Mathematica are so long and rather ugly and hard to read, sometimes you just want to suppress the output. To do that, you can just put a semicolon at the end of the statement and then enter it. And then it still stores the answer in the variable Eigensystem, but it doesn't print it all. Now, if I want to get the eigenvalues of the system, what I can do is I can just ask for the first entry in the Eigensystem, right? Because the first part of the answer, or the result from the Eigensystem function, is in fact the list of eigenvalues. Now, to get the first entry in a list, and by the way, that's what this guy is. This Eigensystem is now a list of 2 things. The first thing is the list of eigenvalues, and the second thing is the list of eigenvectors. I want the first thing, the list of eigenvalues, so the way you do that is you use a double bracket 1, meaning we want the first entry, and then close that with a double bracket. The double brackets are just a shorthand way of getting the first entry in something, the first part of a list. So the first entry in this list is this, and that's the list of eigenvalues. Now I might also want to get, for example, well, maybe I just want the first eigenvalue. Let's see, how could we do that? One other tip, if you want to copy a previous input from the line above, you type Control-L, and that'll just copy the previous input. Now what I could ask for is, suppose I want not just the first entry, which is the whole list of eigenvalues, but the first entry in the first entry. In other words, the first eigenvalue. Then I can say I put a 1 there to take the first entry in Eigensystem, comma 1, and that second one tells me to take the first entry in the list of eigenvalues, right? So it's the first entry in the first entry. And there we go. There it is. Now, let me just take the numerical value. So it's 20.1191. Okay, so you can use this, or show all the digits. So you can use this optional bar to change the way something is displayed. Now, I might also want to know the numerical values of the eigenvector corresponding to that eigenvalue. So how would I do that? Well, for that, I go back to the Eigensystem, which, remember, has stored all the information about the eigensystem of my that is my eigenvalues and eigenvectors of the original random matrix. Now I want the second entry, because the second entry is a list of eigenvectors, and I want the first vector in that list. So I want the first eigenvector, which will correspond to the first eigenvalue. So I do double bracket 2 comma 1 to get the first entry in the second member of the list. So there it is. Now that's still kind of awful to look at. Let's see, can I do anything here? Nah, I don't think so. Let me see. Why don't I do this? What I can do is I can apply the n function. The capital N, just capital N by itself, apply that to anything, and it'll just crunch it down to a decimal number. So it'll get rid of all the formulas. It'll just crunch it down to decimal numbers. So there we go. This is our eigenvector. All right, the first entry is 0.71, second entry 0.84, 1.22, 0.87, and 1 is the last entry in that vector. So you can do that just to get a numerical value, which for our purposes is really all we're going to be interested in, for the most part. We'll do some symbolic stuff occasionally, but for the most part we just want, we can just crunch things down to numbers, right? So if I ask you on the homework to find the eigenvalues and eigenvectors of a 5x5 matrix, definitely use Mathematica. Don't try to do it by hand. And I know that you probably have plenty of questions after this brief introduction to doing eigenvectors on Mathematica. Please bring it up in the help sessions and the office hours and things. Right? I'm happy to go over it then. One more thing I'd like to remark on is a useful fact about eigenvalues, eigenvectors, and independence. So here's a little theorem. It says that basically if you have a set of n eigenvectors, each with a distinct eigenvalue, of course with respect to the same matrix A, then that set of eigenvectors is linearly independent. So basically if we can find a complete set of eigenvectors for different eigenvalues, then we're automatically guaranteed that that will also be a linearly independent set. And so that's a useful thing to know. It's not a difficult proof. We do it by induction in n. Clearly, when n equals 1, one eigenvector always forms a linearly independent set. Right? You can't get any non-trivial linear combinations of a single vector that's equal to 0. So then we move to the induction step. We assume that like the first n vectors, x1, x2, up through xn, assuming those are linearly independent, and then we'd like to show that then the n plus first vector, eigenvector, is independent of the first n. And again, we're assuming that they all have distinct eigenvalues. Suppose, towards a contradiction, that this is not true, and that the n plus first eigenvector is actually dependent on the first n, or in other words, assume that we can actually express xn plus 1 as a linear combination of the first n eigenvectors. Right? Now, because the xn are linearly the first n are linearly independent, the scalars, constants, the ck, c1, c2, up through cn, would be unique. Right? There's a unique way of expressing xn plus 1 in terms of as a linear combination of the first n eigenvectors. Then if we multiply both sides of this equation by a, the left side we pick up a factor of lambda n plus 1. On the right side, each term picks up factors of lambda k, in other words, lambda 1 in the first term and lambda 2 in the second term, and so on. So we pick up a distinct factor in each term. And then dividing through by lambda n plus 1, let's see, dividing through by n plus 1, we can write it this way. We can express xn plus 1 in terms of the first n eigenvectors in terms of these coefficients here. Right? So now the point is, compare the coefficients here that we use to express xn plus 1 in terms of the first n eigenvectors with the coefficients we used up here, c1, c2, cn. They can't be the same coefficients because these ratios, let's see, so over here now, these ratios, lambda k over k plus 1, that relate ck, the old coefficients to the new coefficients, they're never equal to 1, right? Because the lambdas are all distinct. And so that factor is never equal to 1, and so the coefficients down here are never the same as the coefficients up here. But that would be a contradiction, because we assume that the coefficients that we used to express xn plus 1 were unique. Right? That's a consequence of the linear independence of the eigenvectors x1, x2 through xn. Therefore, our assumption that xn plus 1 could be expressed as a linear combination of those n eigenvectors must have been wrong. In fact, xn plus 1 cannot be expressed that way, and therefore, in fact, the complete collection of xn plus 1 vectors are all linearly independent, as desired. Okay, so that's a useful thing to know. Once again, if we can find a bunch of eigenvectors that all have distinct eigenvalues, we can be sure as a fringe benefit that, in fact, all those eigenvectors will be linearly independent of one another.